Okay, good morning, everyone. Welcome to Kinesiology, or 404, Introduction to Epidemiology. Hope you all had a good weekend. I hope you're all having a good week so far. I said earlier, if you hadn't joined, my voice might sound a little bit cracky. My son goes to a babysitter with 2 other kids and came home with a cold. And of course, inevitably, I caught that from him. Thankfully, we all tested negative for COVID and very mild symptoms other than just raspy voice, and maybe I'll cough a couple of times during class while I'm talking. We'll see what happens. So couple of things for today. If you want to follow along for the PowerPoint slides that I mentioned just a minute ago, I posted them on Cougar Courses under this week's section for week number 6. We're in week number 6. We're also in March. So we are coming up on 1 year of our virtual environment of being in the pandemic. And so that's kind of crazy to me. I can't believe that we're already in March and that time is going by so fast. Hopefully, things will continue to get better as the vaccination rollout increases, and hopefully in the fall, we will be mostly in person or have a lot more in-person interactions for our classes and other activities and so on. But I guess we'll just kind of have to see what happens as the vaccination rollout continues and as we see how the pandemic continues to change, especially with the different variants that are arising. So a couple of announcements for today. One, I want to point you all to, again, I've sent you this in email a couple of times, but I'll share it here as well. Don't forget that tomorrow there is a speaker series. So myself, along with a couple of other faculty on campus, typically every semester we host a speaker series. Ideally, these are in person, and we invite speakers from throughout the nation to come to CSUSM to talk about their work in the health field. This one will obviously be virtual because we're still in the pandemic and we're not recommending people travel unless it's essential. But we have Dr. Shawnita Sealy Jefferson, who's coming to talk about her work addressing how structural racism affects health, especially in Black communities. If you attend this session, it's tomorrow from 12 to 1 p.m. You will receive 5 points of extra credit on your exam. So it'll essentially just bump up your exam score by 5 points. So as you know, Zoom tracks how long you're in a session, so you have to attend the entire session. If you log in and log out, I'm not going to give you any credit for just logging in and logging out of the session. If you have to leave a couple of minutes early, that's totally fine as well. The session won't be recorded at the wishes of the speaker, just to ensure that everybody feels comfortable speaking freely and that recording is not going to go out. But she's a really amazing epidemiologist. She's a social epidemiologist. So a lot of what we've been talking about, especially in the second lecture where we talked about social determinants of health and structural racism and how racism affects health, she'll elaborate on her research and her journey through her education as an epidemiologist. So great opportunity to learn from a leader in the field. There will be other events that are similar to this as well. So if you're not able to make it to this one, there'll be at least 1 or 2 other ones later on in March and in April that I'll announce to you all that you'll be able to attend as well. I sent you all this flyer via email. You can go here and register, and you can attend. Hopefully many of you attend, because it will be a really great talk. So that's one thing. And then otherwise, the plan for today is I'm going to go through talking about study designs. That's our introduction to study design is what we have scheduled to introduce today and talk about some new calculations that you'll be required to do for the class. And this is our introduction to how we measure associations, or how we determine things are causally associated with each other in the field of epidemiology. So this is just going to be our first introduction to this topic, and we'll actually build on the study design topics after the midterm, because this is our last lecture of new content before we have our midterm, which is in 2 weeks from today. So that means that next week will be all review. So the live session will I'll plan for it to be around 2 hours. Obviously, you can come and go as you need to if you have other things to do. But I want it to be a little bit longer to allow time to answer questions, to go over sample problems, to help you all work through things that you're not quite understanding at this point, and really do anything else that you think will be helpful for doing well on the exam. So if there are particular topics or questions or things that you're struggling with for the class, feel free to reach out to me before next Wednesday, and I will ensure that I cover those topics for you, but I'll also go through kind of all of the content that we've covered so far briefly to say, here's where you need to focus your studying. So we talked about social determinants of health. Here's how I'm going to test you for social determinants of health. Or we've talked about causal inference. Here's what you should focus on when you're studying, because I realize there is a lot of content. I'm not expecting you all to memorize everything, but there are main concepts and main things that are important for you to know. And so I will kind of point you in the right direction for your studying. Aside from that, I also posted the sample problems for the midterm. And as I've mentioned, those sample problems are what I use kind of as my study guide for the class. What I do, as I've mentioned, is I pull old exam problems, I throw them onto a Word document, I post that. That includes multiple choice questions, true, false questions, and short answer questions. So those will be the types of questions that you will expect to see on the midterm exam itself. So you have those available to you to study from. We'll go through some of those next week in the live session as well. And if there are particular sample problems that you're struggling with that you really want me to go through, send me an email or a message and I will make sure I go through those, because we're not going to have time to go through everything in one review session. But as I've mentioned before as well, I will hold additional review sessions. So we'll have the session next Wednesday from 9:30 to 11:30 a.m. I'll probably hold a review session on Friday, and then I'll hold another review session the following Monday and maybe on Tuesday too. So for those of you who can participate and log into those sessions, I'll be available, and we go through sample problems. We can talk through different concepts that you might be struggling with, and just make sure that you have every opportunity possible to get your questions answered. In addition to that, if you're not able to make any of those additional review sessions, you can email me and we could schedule a time to meet individually to go over the content, or you could even, if you're working in a group or you have friends in the class and you all have some questions that you want to go through together, happy to kind of answer those questions for you too. The midterm exam is going to be a combination of multiple choice and short answer questions. So there'll be about 15 multiple choice, maybe 20 multiple choice questions, and there'll be about 4 to 5 short answer questions, but most of those short answer questions have multiple parts to them, just like some of the homework questions and some of the sample problems that we'll go through, especially today, where you'll be asked to identify a type of study, you'll be asked to do a calculation, and you'll be asked to do an interpretation. You'll have 2 hours to complete the exam. So what will happen is once it goes live 2 weeks from now on a Wednesday at 9:30 a.m., I'll hold a live session. You don't have to attend it, but it'll be kind of like a launch for the midterm and to answer any last minute questions you may have. And then so that during that live session, it'll just be midterms going live. Here's what to expect. Here's what you'll do. And then you'll have 2 days. So from the time it goes live at 9:30 a.m. on Wednesday, what day is that? Let me pull up my calendar. The 17th, you have until Thursday the 18th to complete the exam. But once you start it, once you hit start on Cougar courses, you only get 2 hours to finish it. So essentially what that means is you need to make sure that you're able to complete the exam from start to finish once you click start. And if you want to ensure that you get the entire 2 hours to complete the exam, it automatically closes at 11:59 p.m. on Thursday the 18th. So in order to get the entire 2 hours, you have to start it by 9:59 p.m. on Thursday the 18th. Otherwise, your time is going to get cut short because the exam closes and there's nothing I can do to extend it. So make sure you start it on time, you have those 2 hours. The one thing I will do as well is there's going to be kind of one of the short answers will be a essay type question where you'll have to describe some of the concepts that we've been talking about. I will actually give you the prompt for that next Wednesday. And you'll have the opportunity to work on it before you actually get to the exam, and you'll put your answer on the exam itself. But the idea is so that you're not trying to write out 2 or 3 paragraphs on the exam in a 2-hour period, and that you can think about your answer and have a little bit more time on the exam itself. So then aside from that, because we have problems that you'll be completing where you have to show your work, where you have formulas, you have calculations, for all of those, what I do is you're allowed to do all of your work on a separate piece of paper on your computer, or you're allowed to open up a Word document and do your work there. And what you'll do is once you finish the exam, I'll have a separate link where you'll upload all of your work that shows me how you came up with the answers that you're answering on the exam. That's a required component to get credit for those questions, but also it's an important component of the exam because I give partial credit. So even if you get an incorrect answer and I see the work and you've used the right formula, you've done most of it right, but maybe you accidentally plugged in the wrong number or something happened with your calculation because it didn't work out correctly in your calculator, I will give you partial credit. And I am looking for ways to give you partial credit. So the more work you show me, the better, and the more points you will get. Rarely does a student get 0 points on any individual short answer question on the exam. And the only time that you would get 0 points on a short answer question is if you just don't show me any work and you don't attempt it whatsoever. So before I move on, what questions do you all have about the exam, the format, the review, or anything related? Okay. Hopefully the silence means that all seems very clear and that you don't have any questions right now. But if you do have questions, let me know via email, via office hours, or whatever else. And we'll also talk about the format and stuff a little bit more next week too. So you'll have ample opportunities to ask questions about the exam, to get the help that you need to do well on the exam. My goal is for everyone to do very well. And so definitely reach out to me if you need support or need help or you're not understanding any of the concepts that we've talked about so far. And then aside from that, we do have, you have homework. So your homework number 2 is currently live on Cougar Courses, and that's due this upcoming Sunday. I'll post your homework number 3 today, and that will be due the Sunday before the exam itself. Purpose of the homeworks is to allow you to practice going through the types of problems that you will be tested on in the exams. I am a very lenient grader on the homeworks as well, because I really do want you all to be able to practice and have that opportunity to work through the different problems that we've talked about in class. And then, as I mentioned, there's always the sample problems. Those are not graded. For today's lecture as well, I posted some additional sample problems that will take some time to go over during class today that also have the answers posted on Cougar Courses into this week that again give you an additional ungraded, low stakes opportunity to practice the things that we're learning in the class. So I'm trying to give you kind of different opportunities to go through things. And if there are other things that you need or things that you're still not understanding, just let me know and I'll do my best to try to provide other opportunities for practicing what we're going through. Cool. So as always, if you have any questions, feel free to chime in the chat, unmute yourself, stop me at any time. I'm going to pull up my screen on my iPad so that I can share the PowerPoint presentation for today. Sorry, I'm just making sure that it's actually going to come up. Maybe it's not going to. If not, I'll just pull it up on my computer. Okay, we will stop that for now.
Professor, you're muted.
Oh, sorry about that. Okay, so for some reason it's not working on my iPad. I will pull it up on my iPad in just a moment when I'm going through some of the sample problems, and hopefully it works then. So as I mentioned, today we're going to talk about study design, but we are going to do a little bit of a review beforehand, as I always do. The one thing I also wanted to mention before moving on is that CSUSM, the entire campus, has launched what we call the Campus Climate Survey. So you all should have received an email from University Communications and a video message from President Neufeld that talks about the importance of the Campus Climate Survey. It's a 20 to 30 minute survey that gathers students' opinions on the current campus climate and surrounding, how you feel on campus, what services are available, what experiences you've had on campus, and so on. There are incentives for completing the survey. If you complete the survey, you're entered into opportunity drawings. So for example, if you complete the survey by March 5th, you're entered into a drawing to receive a $50 Amazon gift card. In addition to Amazon gift cards, there's also drawings for AirPods, for gift cards for other places, for parking stickers, for a number of different things. So I encourage you all to complete the survey because I think it's important that we get feedback from students as we define the strategic direction that the campus is going to go. The goal of the survey is to develop an action plan. So based on the feedback and the responses that students have to the questions, the goal is to be able to use that to actually do something to affect change on campus to ensure that we are creating an inclusive and welcoming environment for all students on campus, not only now, but in the future. So if you haven't completed the survey yet, I do encourage you all to do it. As soon as you're able, it closes on March 22nd. So you have the next couple of weeks. So it closes right before spring break, essentially. So make sure you go on. If you haven't received that email, you can, or you have questions about the survey itself, you can email campusclimate@csusm.edu to get more information and get information about what the survey means or how your data is going to be used or anything else. So highly encourage it. This is what we call a cross-sectional study, which we'll actually talk about today a little bit, and I'll talk about how that relates a little bit. Okay, so learning objectives for today. Describe the main goals of study design, the differences between the types of studies, and then the purpose of what we would call descriptive epidemiologic research studies. So before we get to that point, what I wanted to do is a brief kind of review of causal inference. And actually, I was going to try to pull up a couple of polling questions, some of them that relate to causal inference, some of them that go, so there's 4 questions, one that goes a little bit earlier. So based on last week, because you're not able to see the question afterwards, take 20, 30 seconds to read the question before you answer it, and then put your answer in, and then I believe I can at least show you the results, or I can relaunch the poll. A couple of the questions are more basic, and most of them relate to causal inference. First one is just about epidemiology as a whole, just to kind of see where we are. So I'm going to launch a poll with a couple of questions, and we'll start out there. So question number 1, why is epidemiology the foundation of public health? Can you guys see the poll? I don't see anybody answering.
I personally can't see the poll. It's not showing up for me.
It showed
Is
up.
it showing it?
I answered it.
I was able to answer it.
Same here.
Weird. So did it showed up for some people, not others? Some are saying they answered it, but I'm getting 0 responses. Let me try to end it and see what happens. I'm going to try to relaunch it.
Well, for me, my chat is set to just to direct message you, not to everyone. I'm not sure if that's like if that's a thing.
I don't think that should be a thing because this is a poll,
Yeah.
not a chat.
Okay.
Yeah, it shouldn't matter. You should be able to chat with everyone though.
I can see the poll now.
Can you see it? If you all can try to answer it. Oh. There we go. The chat, you should be able to chat with everyone now. I am not getting any responses on the poll though. That's awesome. Okay, well, chat in the right answer. Instead of filling out the poll, what do you think the right answer is? Perfect. Cool. So B is the correct answer. So epidemiology is the foundation of public health because it addresses the core functions of public health. It does have a focus on disease prevention through understanding data and developing interventions, but that's just one component of it. It deals with understanding the distribution of determinants of disease, and it also assesses the health of communities, but really it's because it assesses the 3 core functions. So let's try a second poll. So most causal relationships that operate in chronic diseases are necessary, but not sufficient. You could try to complete it on the poll, but I don't know why it's not working and why I'm not seeing any of the responses. So chat your answers in as well. So most causal relationships that operate in chronic diseases are necessary, but not sufficient. So false. Hopefully you're not just waiting for somebody to respond and then responding in your false answer. That's the crutch of using the chat because you can see everyone's answers. But yes, this is false. For most causal relationships for chronic diseases, they are neither necessary nor sufficient, meaning that there are multiple causes and multiple things that can lead to chronic diseases. And any combination of those potential factors can lead to a chronic disease. Let's do one more. This one's a little more difficult. So this is what is the causal relationship between Hexa and Tay-Sachs? So Tay-Sachs is a rare disease. Everyone with a mutation in the Hexa gene will develop Tay-Sachs disease. All individuals with Tay-Sachs disease have a mutation in the Hexa gene. What is the causal relationship between the two? So someone who answered B, why did you say B? No one willing to talk? So if everyone with a mutation in the Hexa gene will develop Tay-Sachs disease, what does that tell me about the causal relationship between Hexa and Tay-Sachs? Does that tell me it's sufficient or necessary or neither? So everyone with a mutation in the Hexa gene will develop Tay-Sachs. No one wants to chime in?
I mean, yeah, it's sufficient, right? Because one causes the other, or like it relates to it.
So it's sufficient, correct? So because
Yeah.
if you have the Hexa gene, you're going to develop Tay-Sachs. So that means just having the Hexa gene is sufficient to develop Tay-Sachs.
Yeah.
And then, so great, Randall. And then all individuals with Tay-Sachs disease have a mutation in the Hexa gene. So what does that tell us?
It's necessary.
That it's necessary. Yep. So in order to have Tay-Sachs disease, you have to have a mutation in the Hexa gene. So it's necessary. So all of these types of problems, and I realize these are a little bit confusing, all of them are going to have two components. One component of the problem is going to tell you about whether or not the causal relationship is necessary or not. And the other component of the problem is going to talk about whether or not it's sufficient or not. So in this case, this first part, everyone with a mutation in the Hexa gene will develop Tay-Sachs disease. That tells me about sufficient. And because everyone develops Tay-Sachs disease, if they have a mutation in the Hexa gene, that means that just having that mutation is sufficient for a person to develop Tay-Sachs disease. And then all individuals with Tay-Sachs disease have a mutation in the Hexa gene. So that means that no one without a mutation in the Hexa gene has Tay-Sachs. So in order for Tay-Sachs disease to present, there must be a mutation in the Hexa gene. So that tells me that that mutation in the Hexa gene is necessary. So then that tells me that the causal relationship is necessary and sufficient. So anytime you read one of these types of scenarios, break it down into those two parts. And what is it telling you? If instead I said, people with a mutation in the Hexa gene might develop Tay-Sachs disease, but most people who have that mutation will never develop Tay-Sachs disease. That would tell me that it's not sufficient because most people are not developing Tay-Sachs disease in the presence of that Hexa gene. If I said there are Hexa gene mutations may lead to Tay-Sachs disease, but there are also other gene mutations that could lead to Tay-Sachs disease as well, that would also mean it's not necessary. So you're kind of looking for that language and what it's talking about and how they're related to each other. Just make sure you're reading what I'm giving you carefully. There'll at least be one or two problems that are similar to this on the midterm exam where you'll have to determine the causal relationship between two different factors. All right, so let me pull up the slides so we can start going through the actual PowerPoints for today and get to some sample problems in just a few. So as most of those sample problems that we just did in the poll went through, the aim of epidemiology is to determine the causes of disease in the population. And so our real goal is causal inference, which is making a conclusion about why a disease exists. So if someone has Tay-Sachs disease, what's leading to that Tay-Sachs disease? If someone has diabetes, what's leading to that person having diabetes at that moment in time, or really any other disease? Causal inference provides a scientific basis for understanding the etiology and development of disease, and for also developing interventions and public health action to ensure that we are providing the right resources and addressing the right factors that can have the biggest impact in the population. Our goal in public health as epidemiologists is to identify things that we can intervene on that will help the largest number of people possible. This might be slightly different than the goal of medicine or that doctors have, where they're looking specifically for the patient that they have in front of them at that moment in time. What can they do to intervene to either prevent disease or to treat disease? And so what we're looking for in public health is, how do we affect a large group of the population and develop programs and resources available so that people can be as healthy as possible? So if we're trying to prevent things like type 2 diabetes, if we know that physical activity is a potential cause of type 2 diabetes, where if people are not physically active enough, it increases their risk for type 2 diabetes, then we want to create an environment where people have the ability to be physically active on a regular basis, because as we increase physical activity levels in the population as a whole, we will decrease the number of cases or the incidence and prevalence of type 2 diabetes in the population. So that's the perspective that we're typically thinking about in public health, is how do we make the biggest amount of change? Part of this idea of causal inference, what we talked about, is we use what we call this sufficient component cause model, where we have these causal pies. And within these causal pies, we have different components that can lead to disease in a particular individual. So if these 3 pies indicate 3 different people with the same disease, it might be that person 1 only has component A and has disease. Person 2 has components B, C, and D and has disease. And person 3 has B, G, E, and F and has disease. All of these are components of an individual's disease. If a particular component is part of every individual's disease, so say every person who develops type 2 diabetes is physically inactive, which that's not the case, but if every person who developed type 2 diabetes was physically inactive, that would mean that physical inactivity is a necessary component of all people's diabetes. But if that's not the case, then that would mean it's not necessary to be physically inactive to develop type 2 diabetes, that there are other factors such as diet, family history of diabetes, age, and a number of other things that can lead to type 2 diabetes as well. And then that sufficient component is if that component is present and disease happens, then that means it's sufficient for disease to happen. And so that's what we think about in terms of how are we understanding how diseases occur in our population. And as I've mentioned, and as we just went over, there are different types of causal associations, necessary causes and sufficient causes. A necessary cause means that the cause must be present for the outcome to happen or for the disease to happen. But just because that cause is present does not mean that the outcome is always going to happen. A sufficient cause means that if the cause is present, the outcome must happen. But it is possible that the outcome can happen without that cause present, meaning that there might be other things that can also lead to disease. So there are sufficient but not necessary components of disease. There are necessary but not sufficient component of disease. And then there are also necessary and sufficient, or neither necessary nor sufficient components of disease, which is what we look for. We look at in most chronic diseases. And for most infectious diseases, they're necessary but insufficient, because not everyone with a virus or a pathogen or a bacteria is going to develop clinical disease. So how do we assess causal inference in public health, and especially in the field of epidemiology? And we do that through conducting research studies. And we do that through a rigorous scientific process where we conduct multiple different types of research studies to move from understanding associations or correlation between some exposure and some disease outcome, and moving into understanding disease causality. And so on this slide, what I have is the 2 major areas of research studies that we have and that we use in epidemiology and in research as a whole to understand disease causation. Starting out with, on the left-hand side, descriptive studies. And so descriptive research studies are really where we're looking at descriptive epidemiology. They answer the questions what, who, where, and when. And these include things like case reports, case series, ecological studies, and cross-sectional studies, which we'll talk about today. And these are purely correlational or descriptive studies where we are just trying to describe what is going on in the population, but we can't make much inference about causation and disease causality from descriptive studies. To determine disease causality, we have to move over to what we call analytic research studies or analytic epidemiologic studies. And those are moved into, carried into two different bends. There's observational research studies and there are experimental research studies. Observational analytic epidemiologic studies are ones where we are just observing the world as it happens. So what that means is that we're not intervening or manipulating participants in our study in any way. Rather, we are just examining what exposures they have, what behaviors they're engaging in, and then we're also examining what health outcomes they have. We can use observational studies, and there's a hierarchy of observational studies to test hypotheses about why disease is happening and how disease is happening. However, there are always going to be limitations in observational studies and really in all research studies in terms of the amount of evidence that they give us about why disease exists and what we can do to prevent disease in the population. And so we'll talk today a little bit about cross-sectional studies, which are both descriptive and analytic studies. But then after the midterm, we'll talk about cohort studies and case control studies in more detail after I introduce kind of what they are today. And then we'll have a lecture on experimental studies as well, which is likely what you're all most familiar with an experimental study being defined by the fact that we are manipulating something, meaning, for example, clinical trials for vaccinations. Those are all experimental analytic studies where we are testing the efficacy of a vaccine to prevent novel coronavirus infection. And so that certain people were randomized either to receive the vaccine or to receive a saline placebo. And we wanted to see whether or not the incidence of COVID-19 infection was lower in people who received the vaccine compared to people who received the placebo. And so that's what we would call our gold standard for conducting research studies for understanding causality. So we know now from those clinical trials that getting the COVID-19 vaccine, it prevents COVID-19 infection at a really high rate. But more than that, it prevents almost all hospitalizations and all deaths. And we know that from a rigorous process of testing the efficacy of that vaccination in a large group of our population. So we'll talk in more detail about how we go through and the different levels of experimental studies after the midterm in more detail. And one thing we'll talk about is there are different levels of experimental studies and they're not all treated the same. And that goes from quasi-experimental all the way up to double-blind randomized controlled trials, which is what we're all probably most familiar with and hear about most often when we're thinking about drug treatments or vaccinations or so on. So as I mentioned, there's kind of this hierarchy that we use when we're trying to determine disease causality. And what the ultimate goal is how do we change public health messaging to prevent disease? How do we affect clinical practice guidelines to ensure that patients are receiving the right care and the right treatment for their particular disease? And how do we inform the messaging that we need to give to people to protect their health? We would never inform messaging from a clinical practice or from a public health practice standpoint based on animal or laboratory studies. Those are studies that are done to first examine what we think is happening. And then we move into additional studies like case reports, case control studies, cohort studies, randomized control trials to determine how those findings change over time and through doing different types of studies to understand what's really going on. And we only make recommendations for health or recommendations for behaviors when we have enough evidence to determine that that is the best decision or the best recommendation at that time based on the evidence that we have. So that means we would never make a recommendation based on one singular study or based on an animal study or an uncontrolled study, because that doesn't provide enough information for us to truly know how some exposure might affect disease, and can be very problematic because that means that people might not trust the information that researchers are providing if those recommendations then later change. And we've seen that happen in the last year, unfortunately. And I've mentioned this before with masks, where when the pandemic first started, the use of masks was not recommended. And that was because we did not have enough evidence about how COVID-19 was spread or about how masks could potentially protect people from COVID-19. And until that evidence was developed, that recommendations for wearing masks wasn't given because they didn't want to mislead the public to think that masks were going to protect them. But unfortunately, what happened was that messaging got really messed up and the right types of communication weren't given. And it was initially said, don't wear masks, they're not going to help, as opposed to, we're not sure what the role masks might play. We're going to do some research over this next few months to determine what recommendations we should make for the use of masks. This doesn't mean that they don't work. It doesn't mean that they do work. It means that we need more evidence to provide the right recommendation. And that's where communication surrounding things that affect our health is extremely important, because mistrust in science, and we've seen this happening a lot over the last year, is continuing to build in our society. And the more that people don't believe in the way that science is conducted and the information that's coming out of it, the harder time we're going to have to get people to get vaccinated or to engage in public health practices that not only protect themselves, but also protect the communities and the people that surround them. That's a whole other field that I think is extremely important component of medicine and public health, is communication and marketing, and how do we actually get the right message out. And unfortunately, what we see happening, as I've mentioned before, is a lot of research is picked up in the media, and studies that shouldn't be talked about in the media are talked about as if we've found this next discovery. So last week, I showed you that article on wearing glasses and prevention of COVID-19. Based on a singular, uncontrolled, preliminary preprint study that didn't have really compelling evidence that wearing glasses could prevent or protect people from COVID-19. But yet hundreds of media sites picked that up and wrote articles about it. And that's very misleading for the public. And if new studies come out and say glasses don't work, it's not going to protect you from COVID-19, then that creates a mistrust in the process and how we're understanding science. So that becomes very problematic in many ways. So that's one thing I want to talk about throughout this semester, and why I focus on study design and what the different studies are and how we can use them, because hopefully it will give you some of the tools that you all need to examine the research that's out there and understand what it actually means and how we can use that information. So this figure just kind of depicts the different types of studies, where we start out, and I'm not going to really go through this, but a large part of what defines the different types of studies is how we collect data and when we collect data. And you'll kind of see that as we talk about the different studies as we move forward. So first example that we'll talk about today, before we go through some sample problems, I'm going to introduce you to case reports and case series, ecological studies, and cross-sectional studies, and then we're going to do a couple of sample problems. So case series and case reports. So you've probably seen, or you've probably heard about a lot of different types of case series or case reports, but maybe didn't actually realize exactly what they were. Here's an example of a case report for COVID-19 from May of 2020. So just a couple of months after the pandemic happened. And what this case report is describing is a singular patient who had symptoms of COVID-19, what those symptoms look like, and what treatment they received, and how they responded to that treatment. So that is a description of a singular person and what their particular disease prognosis looked like, what their symptoms were, what their treatment was, and how they responded to it. So that's a singular case report that doesn't tell us anything about disease causality, but is really meant to just describe what is going on. And usually case reports and case series are used to describe something new. So something that we haven't experienced yet for health, and that we want to say, what do these things look like in our population, and what do we need to do further in our research to understand why this is happening? So a couple of other examples, for example, case series surrounding the Olympics in Brazil a few years back, where we had the Zika virus epidemic or outbreaks. And we had a whole large number of women in Brazil who were having babies with microcephaly, or underdeveloped head and brain, and had a lot of other birth defects. And so what they had initially done is, when they started to see women having babies with microcephaly, they tried to describe the similarities between those women. And then they eventually identified the Zika virus itself in those women, and were able to pinpoint that as the exact cause, or there's called a teratogen, or a factor that causes a birth defect that led to these women having babies with microcephaly. And so then that led to the public health recommendations that women who are pregnant or who are planning to become pregnant shouldn't be traveling to regions where Zika virus was endemic, or where it existed and where they could potentially become infected, because that would put their unborn babies at risk for birth defects. And so that was an important step to making public health recommendations, was developing these case series to describe the presentation of disease, and the fact that all of these women who had babies with microcephaly had the Zika virus. And then later studies were done to actually confirm that in different settings, and to examine how and when infection with Zika virus during pregnancy, how that impacted the birth outcomes. Because, for example, if that Zika virus infection happened during month 1 of the pregnancy, the outcomes for the birth might be different than the Zika virus infection happened during month 8 of the pregnancy, because of the different developmental levels that happen at different stages. And so these case series became an important part of understanding Zika virus and what that meant for birth outcomes in women. And then some other case series looking at fasting and cancer treatment in humans. So this was just used to examine how, if humans fasted, what that meant for their cancer treatment, or if they were fasting during cancer treatment, what their outcomes were. And the goal of this, and the reason that you would do a case series instead of an experimental study, is because we need to develop evidence that these types of things are safe before we do an experimental study where you group people and say, you're undergoing cancer treatment for this cancer, you're going to fast, you're not going to fast, and we're going to determine your long-term outcomes for your cancer treatment. If we don't know that putting people into those groups to determine how that affects their outcomes is safe and potentially effective, if we don't have any evidence that it might work, it becomes unethical for us to put people into groups not knowing what's going to happen. So we can describe that in a series of people who are doing that already and say, this was safe, this is what their outcomes were, it looks like maybe fasting might be beneficial during periods of chemotherapy. So now let's further test that in additional studies to see how fasting affects cancer treatment outcomes. So as I said, a case report involves a profile of a single individual. A case series involves a small group of patients with a similar diagnosis. These don't tell us anything about disease causality. They're often used for emerging diseases or conditions to first describe what's going on, and they provide evidence for larger scale studies and a basis for developing hypotheses about what's going on with disease in our population. So the next thing I wanted to talk about is what's here on the slide. So there's a couple of figures here. And the question for you all is, what conclusion would you make based on these figures? So I'll just orient you to these just briefly. On this top left figure, The y-axis is the percent wearing masks most of the time or all of the time in public. So this is by state. So each of these dots represents a different state. And this is the current COVID test rates from October 7th, 2020. So this is a study from last fall. And they looked at the percent of people who reported wearing masks all of the time or most of the time in public related to the number of new cases per 100,000 people in the population in that state. And then, so that's the top figure. And then these bottom two figures, whoops. The left-hand side is the percent wearing mask in public most of the time or all the time. And then the right side is the percent of people who know someone who is sick with COVID-19, with the darker colors on both of these indicating higher percentages. So based on these two figures, what do you think this information means about mask wearing?
Masks are effective for those like in the West and on the coast, I guess. Like, I don't know.
No, that's great. So what else though? So based on this, so this is one study. Can we say that masks are effective?
Yeah.
Why can we say they're effective based on this?
We can see.
Oh.
Oh no, sorry, go ahead.
I was just looking at the map, and like the areas that are lighter are darker on the people who know someone who's sick.
So the lower the percent of mask wearing, the higher percent of people knowing someone who is sick, is what you're observing in the two maps in the bottom. Okay. And Mike, what did you have to add?
I was just going to say, we can see that the states with the highest distribution of mask wearing also have the lowest distribution of knowing who someone is sick. So if you take a look at California, it's like a dark blue, indicating that we wear masks most of the time. And then we also have a light peach, indicating that we have a lesser percentage of someone who we know is sick. So there's that correlation between mask wearing and less cases.
So there's a correlation that we can see in these graphs. Does that mean that wearing a mask prevents COVID-19 from this data? So do we, and I guess my question for you all is, do we know that the people who were wearing masks were the ones who weren't getting COVID-19, or the people who weren't wearing masks were the ones who were getting COVID-19 based on this data?
No, it doesn't tell us if the ones who were wearing masks got it or vice versa. It just tells us who's using the mask and who's not.
Yeah. So this data comes from what we would call an ecological study. So what an ecological study is, and I have it on the next slide, it's an observational descriptive study that's defined by the fact that data is analyzed at the population level rather than the individual level. So what that means, in using these figures and graphs as an example, is that we're comparing percent of mask wearing in the entire population to percent of knowing someone who is sick in the entire population in those states. And based on that, you can make an assumption that where there's more mask wearing, there's less disease. But the problem with that is that the level of evidence that we have here is limited, because, and something that you don't know about these figures is that this data doesn't come from individuals. They didn't go out and ask people, did you wear them? How often? So they had, in general, in the whole population, how often do you wear a mask? But what they didn't know was whether or not the people who wore the masks had ever been infected with COVID-19. What if someone got COVID-19 and they only started wearing a mask afterwards? So now we have this reverse causation where the COVID-19 actually led to the mask wearing, and not the mask wearing led to a prevention of COVID-19. So we don't actually know enough about individual behaviors or what's going on in these particular figures, because we're looking at data at the whole population level and not looking at individuals themselves to say what's going on, and if you wear a mask, are you less likely to develop COVID-19? We know that from other research studies, but this particular study was a ecological study where they're comparing groups or states to each other, and they're comparing rates of disease and rates of mask wearing between states. This can be used to then prompt hypotheses to say, all right, we see in areas where there's more mask wearing, there's less disease. So now let's go and do an experimental study, or let's do a cohort study where we follow people forward and we say, you wear a mask every time you go in public, and we're going to follow you for the next 2 months, and we're going to see the people who wear a mask every time they go in public compared to the people who don't wear a mask when they go in public, who gets disease. And so we can follow people and say, this is what it looks like when people are wearing masks versus not wearing masks. But based on this data, we can't actually make that conclusion. We can just develop that hypothesis that masks might be protective at this larger level, but we don't know anything about anyone in the population as a whole. So these ecological studies are defined by the fact that you're using data at this population level to make comparisons between states, between countries, between cities, to understand what might be going on. These types of comparisons are really good for developing hypotheses and understanding how policies might affect health. So for example, if California develops a policy about smoking and that you can't smoke indoors, which California was the first state to do so, do we see our rates of lung cancer decreasing as a result of secondhand smoke exposure because we have made it illegal for people to smoke indoors when we compare to other states who didn't do that? So it allows us to compare overall rates of disease between those populations without actually having to collect information from individuals in the population for our study. So they're really good at collecting information quickly and developing hypotheses, but they're not great at actually identifying causation. We can only look at correlations and do further study to examine what's really going on, because we can't assess the timing of disease. So I mentioned that, what if someone got COVID-19 and started wearing a mask? That's the reverse of what we want to see happening and what we would expect, right? And so because we can't assess that timing, it limits the interpretations we can make. And then there are also there are problems with what we call ecological fallacy, where you make observations at the group level in these ecological studies, and you try to ascribe those observations to the individuals in the population without knowing anything about the individuals in that population. So that ecological fallacy creates problems in terms of how we interpret data when we're collecting it at the group level. And we have a study at the group level, knowing nothing about the actual individuals from whom that data came from. So that's an ecological study. And then the next one, you're probably not going to be able to read this unless you have it really large on your screen, but I just wanted to show you an abstract from a study. And this study was used to examine partnership health associations among transgender individuals using the Behavioral Risk Factor Surveillance System, or BRFIS. And BRFIS is actually a surveillance system that is developed by the Centers for Disease Control and Prevention to examine the health of the population of the United States as a whole. In this particular study, what they looked at was whether or not if a transgender and a gender nonconforming individual had a partner, so that whether or not their health was affected by having a partner versus not having a partner. And what they found was mixed findings in that trans women, that partnership among trans women predicted better general health, less depression, less smoking and heavy drinking, and having health coverage. The impetus for this study was that in cisgender couples, that we find that typically people who are in relationships are healthier. There's a number of reasons why, and that's not always the case, where there are oftentimes, especially if the relationship is not a healthy relationship, that being in a relationship can be, people are unhealthy for a number of reasons. But looking at how that essentially what the goal is, how social support affects health. And so they found, among trans men, partnership predicted only decreased likelihood of recent medical checkup, but these provide evidence of the first multi-domain partnership health associations for transgender and gender nonconforming individuals, understanding how partnership might affect health as a whole. And it points to the needing of more research. So why they're pointing to the needing of more research is that this is what we would call a cross-sectional study, where what they did in this particular study is they asked people about their gender identity, and people were identified as cisgender, transgender, gender nonconforming, among others. And then they also asked people about their health. What's your general health? When's the last time you went to the doctor? When's the last time you went to the dentist? And a number of other things. And they asked them those questions on the same survey at one point in time. And then they did an analysis to examine how they're associated with each other. And so that's the goal of the BRFIS surveillance system. And there's a number of other large scale, what we call cross-sectional studies, where we're examining just what does the population health look like at that moment in time. These are used as well to develop hypotheses to understand if we see that support from a partner improves health among transgender and gender nonconforming individuals, then how can we develop interventions to provide the right type of support to protect the health and improve the health of transgender and gender nonconforming individuals? And then that additional research doing larger scale studies would provide more evidence surrounding this. So as I mentioned, this is a cross-sectional study. These are also called prevalence studies. What that means is that they're typically used to examine the prevalence of disease in the population. So last week I showed you those maps of obesity and overweight in the US. Those come from the BRFIS system as well, where people are asked about their weight and their height and their sex and their gender and so on. And then they use that to calculate BMI. So that is used to then examine the prevalence of diabetes or of overweight obesity. They ask questions about diabetes, about heart disease, and so on. So anytime you see from the CDC or from another source, this is the prevalence of diabetes in the population. This is the prevalence of heart disease in the population. That information typically comes from large-scale cross-sectional studies that are asking people about their health status overall. And so what defines these studies is that they're asked about their health status and about behaviors they engage in at the same time. And these can be descriptive or analytic studies, and they provide a snapshot of the population and what's going on in our population as a whole. We can generate hypotheses from these types of studies, but we cannot assess timing of disease. So for example, if on a survey, so these are usually done with surveys, if on a survey someone says, I never work out, so I work out 0 times per week, and then they also say I have type 2 diabetes, we can do a study and see that physical inactivity is associated with type 2 diabetes. But what we don't know is whether or not that person was diagnosed with type 2 diabetes and then they stopped working out, or if that person wasn't working out and they developed type 2 diabetes. It doesn't tell us anything about the timing. We then have to take that information and do additional research studies, what we call cohort or longitudinal studies, to examine whether or not that behavior came before the development of disease. And we'll talk about that after the midterm. So these are useful, as I said, for developing hypotheses and understanding kind of that first correlation or association between exposure and outcomes, but they're not great for disease causality. So these are all descriptive epidemiologic studies that are used to describe the distribution of health and disease in the population and potential associations between risk factors and disease, and what groups might experience disease more than other groups. So descriptive studies are really good for describing health disparities and understanding where we might need to allocate resources. They give us clues to the causes of disease, but are limited in our interpretations, but they're good for generating hypotheses. So when we think about causality, what we want to think about is that if we're looking at ecological studies where we're plotting health in different areas or over time, that gives us information about probable determinants of disease. So for example, if a disease is only happening in the summer, then that tells us that we need to search for causal factors in the summer. for that disease. And if we did a research study in the winter, we wouldn't really be able to examine much about that particular disease. And doing those geographic comparisons allow us to identify those large structural factors that might differ between states or countries or different regions within a state to understand where we can intervene to protect the health of a large group of people in the population. So next part of this, before I jump into it, let's take like a 3-minute break. And then the next thing we're going to do is a couple of calculations, but what questions do you have for me before we do that? Cool. Let's take a break until 10:40. I know it's a short break, but I want to get through a couple of calculations, and I'm going to try to get my iPad up and running really quickly because that'll be helpful for me. But the next step that we're going to do is we're going to talk about how do we actually measure associations in cross-sectional studies specifically, and there's 2 different measures that we use. So 10:40. Recording, because last week I forgot to restart the recording after we paused. So I don't want to do that again. So the next 20-25 minutes, we're going to talk about calculations and how we examine associations using cross-sectional studies. We're not going to talk about calculations for ecological studies or case reports or case series because they're not used as commonly or as relevant for a lot of what we'll talk about moving forward. But there's 2 types of calculations that we use for cross-sectional studies, and those are called the prevalence ratio and the prevalence odds ratio. And what you're going to get very comfortable with for the rest of this semester is using what we call a 2x2 table to determine associations between disease and exposure. And so what you see here in the middle is a 2x2 table, and I'm going to kind of walk you through what is in this 2x2 table, how we calculate prevalence ratio and prevalence odds ratio, and then we'll go through an example together before I have you all work on an example on your own. So prevalence ratio tells us how large is the prevalence of disease in one group compared to another group, and the prevalence odds ratio tells us the odds of exposure among those with disease compared to the odds of exposure among those without disease. They're very similar to each other, but you'll see some examples of how they're slightly different and why that interpretation of the difference matters. These formulas are already on your formula sheet that's posted on Kruger Courses. The other thing that's posted on Kruger Courses under the resources is interpretations for these formulas, because you're always going to have to write out sentences of this, we found that this is associated with this or blah, blah, blah. And those, there's certain structures that are ideal when you're writing out those sentences that I give you the format for those, and we'll talk about those moving forward. So this 2x2 table, the reason that it's called a 2x2 table is because there are 2 columns and 2 rows. So that gives us 4 cells in here, with this first column always being disease, second column always being no disease. So say we were looking at what factors were associated with type 2 diabetes. This first column would be type 2 diabetes, and this one would be no type 2 diabetes. And the rows, the top row is typically always going to be exposure. The bottom row is going to be no exposure, but that can be defined in different ways, and you'll see in some examples how that changes. But essentially, say we're looking at physical activity and diabetes, then my exposure could be physical inactivity, and my no exposure is physical activity. And then what we see is contained inside of these boxes, and what you're going to have to do based on some scenarios that I give you. Cell A is everyone who has our exposure of interest, who also has our disease of interest. Cell B is everyone with the exposure, but who does not have the disease. Cell C is everyone with no exposure and disease. And cell D is no exposure, no disease. And then all the outside totals are just the combination of A plus B, the total here, is everyone with exposure. C plus D is everyone without exposure. A plus C is everyone in my study with disease. B plus D is everyone in my study without disease. And then the total number of people in the study just gets put on the bottom right-hand corner. And you'll see in the calculation formulas that are given below, once you fill in the 2x2 table, the numbers that are in each of those cells are used to actually do the calculation. So the prevalence ratio is equal to the prevalence of disease in the exposed population. So that's this top row. So this is getting a little bit messy, where prevalence of disease is A over A plus B. So that's everyone who has the disease over everyone who has exposure. Prevalence of disease in the non-exposed group is everyone who has disease, or C, over everyone who does not have exposure. And so then to calculate that formula, you would just do A over A plus B, and that'll give you a number. For your prevalence odds ratio, you just multiply A times B divided by B times C. So I'm just going to walk through an example of what that looks like right after I kind of give you what these mean. But you're going to come up with numbers. These prevalence ratios and prevalence odds ratios are going to range anywhere from 0 to 3, 4, 5. They can be really high, but typically we don't see them higher than 3 or 4 or 5, but sometimes they might be 10 or 15. But if a prevalence ratio or a prevalence odds ratio is equal to 1, that means that there's no association. That means that there's no relationship between your exposure and your outcome. If your prevalence ratio or your prevalence odds ratio is greater than 1, that means there's a positive association. So that means that the prevalence of disease is higher in the people who are exposed than the people who are not exposed, or the odds of disease is higher in the people who are exposed than compared to those who are not exposed. And if it's less than 1, that's what we would typically call a protective factor. So that means that if someone is exposed to that particular factor, say they're physically active, they might have a lower prevalence of type 2 diabetes than people who are physically inactive. So it's protective against that particular health outcome. And so then to illustrate all of this, let's go through an example. Researchers wanted to determine if family history of depression is associated with depression. To answer this question, they recruited 1,500 people to fill out a screener to assess whether they have depression and asked them about whether they have a family history of depression at the same time. In total, 125 people were screened as being clinically depressed, and 475 people indicated that they had a family history of depression. Of those with a family history of depression, 75 were screened positive as depressed. Of those without depression, 400 indicated that they had a family history of depression. So you're probably thinking, oh no, a word problem. There's a lot of information in here. There is, but it's pretty easy to break down to pick out what information you need. And you're going to see a lot of word problems throughout this semester. So it's important that you're able to identify what pieces you need from this. So we want to know, is family history of depression associated with depression? So first question I have for you, based on this scenario and what you were just told, what type of study is this based on what we've just talked about today? And how did you determine
that? Cross-sectional study, or
yeah,
is that what you're asking for? Okay.
Yep, cross-sectional study. And how did you determine it was a cross-sectional study?
There's like 2 factors, so depression and then a family history of depression.
So family history of depression and depression. And the key thing that you're going to look for, because you're going to get scenarios and you're going to have to tell me what type of study it is that they asked about depression and family history of depression at the same time. So that means it was asked on one survey at one point in time to examine the association between family history of depression and depression. So now in order to examine whether or not family history of depression is associated with depression, I am going to create a 2x2 table. The first thing I need to do is label that 2x2 table. So my outcome, or my disease in this case, is depression. And it's going to be yes, depression. And I'm just writing it out this way. You could put no depression, depression, no depression too, but for space, and no. So this left column is everyone who does not have depression or has depression. The right column is everyone who has depression. And my exposure is family history of depression. And I'm going to put yes on top and no on bottom. So now that I have that set up, it says to answer this question, they recruited 1,500 people to fill out the screener. So I'm going to put 1,500 on my bottom right-hand corner. And then they asked them about family history of depression. In total, 125 people, and I'm going to label these, were screened as being clinically depressed out of the 1,500. So where in my 2x2 table does that 125 people go, or where kind of on my screen?
That should 125 should be on the A block, I think.
Not the A block. It's 125 being clinically depressed out of the 1,500. So it's not C either.
A plus C.
So A plus C. So that is everyone who has depression in my population. 125 people. And then 475 people indicated they had a family history of depression. So where is, as a whole, family history of depression indicated on this?
A plus B.
A plus B. So does everybody see that? Where 100, so everyone in this yes block here, that's all the people who have that condition. Everyone here, that's everyone who has a family history of depression. And then now it says, of those with a family history of depression, 75 were screened positive as depressed. So where does that 75 go?
A.
Perfect. And then of those without depression, 400 indicated they had a family history of depression. Where does that go?
B.
B. So now we have enough information here to finish filling out the table. So if 125 people in total had depression and 75 had a family history, then that means that 50 didn't have a family history of depression, but had depression. And if 1,500 people, we examined 1,500 people, 125 of those had depression, we just do 1,500 minus 125. So that gives me 1,375 people as having a no depression. And then we can do that same thing for the other column where this is going to be 1,025. And then we do 975 here. And then what you should be able to see is all of these numbers should add up. 75 plus 400 equals 475. 50 plus 975 equals 1025. 400 plus 975 equals 1375, and so on. So now I have filled in my 2x2 table, and I want to know what are the odds of a person with depression having a family history of depression. And so I'm going to calculate my prevalence odds ratio, and that is equal to AD over BC. So in order to do that calculation, you just plug in the numbers. So 75 times 975 divided by 50 times 400. And that is going to give me, I need my calculator because I definitely can't do that in my head. 3.65 or 3.66. So what that tells me is that among those who had a family history of depression, and I'll write this down in a minute, had a 3.66 times higher odds of being depressed than those who didn't have a family history of depression. So I'll type that out right now in the chat in a second. The other thing I wanted to quickly show you too, though, so I gave you two different calculations. You can also calculate the prevalence ratio. The formula for prevalence ratio is A over A plus B over C plus D. And again, you're always going to have these formulas when you're doing these calculations. So the calculations themselves are not very difficult. The difficult part is ensuring that you're plugging in the numbers correctly in the 2x2 table. So then if I did this, I would do 75 divided by 475 over 50 divided by 1025. And then 75 divided by 475 over and that equals 3. Let's see, I just got to notice that my screen sharing stopped even though it's still showing up. That equals 3.24. So what I'm going to do really quickly is I'm going to chat with, I'm going to chat in the interpretation of these. So that you'll see though that 3.24, and I don't know why, there it goes. So let me try to re-pull that up. The 3.24, the prevalence ratio is slightly different than the odds ratio. That's always going to be the case where they're different from each other. They'll get more similar as the prevalence of disease becomes more rare. So if you have a really low prevalence of disease, your prevalence odds ratio and your prevalence will be very similar to each other. But that's not really a level that you all need to know for the class. I just wanted to mention that. I will always tell you what to calculate, whether I'll tell you calculate a prevalence ratio or calculate a prevalence odds ratio for cross-sectional studies. So again, what this means is if I'm interpreting the prevalence odds ratio, so I'm going to type it in, who have a family history of depression have a 3.65 times higher odds of depression compared to those without a family history of. So those with a family history of depression have a 3.65 times higher odds of depression compared to those without a family history of depression. Technically, the interpretation for a prevalence ratio is slightly different, and it would basically just be this, and there's only really one word that's different. Those with a family history of depression have a 3.24 times higher prevalence of depression compared to those without a family history of depression. And that's really just based on the fact that in one calculation, we're comparing the prevalence, how large is the prevalence in one group and the other, to the odds of exposure. So one of these, the prevalence ratio is telling us essentially the prevalence is higher in those with a family history of depression compared to those without. The other one is telling us if you have a family history of depression, you're more likely to have depression yourself. That's a really nuanced difference that I don't expect you all to know how to interpret, but I just like to give you all that information. So if you see these, you know what they mean. So any questions about those calculations or those interpretations? And I'll pull up another example. Okay. So one more example, and this example, so as I mentioned on Cougar courses, there are sample problems that you can go through that are under this week's lecture. They're separate from the exam sample problems. So if you can go and download those sample problems. I'm going to stay on here about 10, 15 more minutes so we can get through this. If you need to leave, that's totally fine. But download those sample problems. I'll keep this up as well. Go through, try to fill out a 2x2 table. I can open up some breakout rooms if you would like to go to a breakout room to work on this with some other students, but I have gotten a little bit of feedback on the form that you all completed last week. And if you haven't completed the feedback form, please do so. That sometimes in the breakout rooms, nobody talks. So you're all just kind of sitting there waiting for someone else to talk, which that's not the whole purpose of them. It's to work through problems to make sure you're understanding it. But I'll open up some breakout rooms. If you want to go into the breakout room because you want to work with someone, go right ahead. I'm going to assign the breakout rooms automatically, but you can actually jump between the rooms. So if you want to move rooms, go ahead or come back out to the main room and move to a different room where there's other people if no one goes to your particular room. Or like I said, you could stay here, work on this for about 5 minutes, and then I'll go through that problem on my own as well. Sorry, my screen sharing keeps stopping on the iPad. So let me show you the problem. And again, if you go to a breakout room, you're not going to be able to see this PowerPoint. So you have to go to Cougar Courses and download the exercise. And this is part of the part B, number 1 on the exercise. All right. So let me know if you have any questions. Just a few more seconds and everyone will be back. Okay, so scenario says, I know that probably wasn't enough time to go through everything, but hopefully you've been able to set up most of it and you could finish it up as we walk through this. But nationally representative household survey was conducted in South Africa from March to August 2003 to assess the relationship between condom use and HIV among women in a study on HIV. In total, 4,063 women completed the survey and 788 indicated they were HIV positive. Among those who were HIV positive, 355 indicated they used a condom at their last sexual encounter. Among those who were HIV negative, 1,598 indicated they used a condom at their last sexual encounter. Create a 2x2 table, calculate the prevalence odds ratio, and interpret it in a sentence. So I have my 2x2 table. What goes on my columns for my 2x2 table here?
On the top, it's HIV positive on the left, and on the top right, no HIV.
So HIV positive, negative. And then on the rows, what goes there?
The top would be condom and the bottom would be no condom.
So one thing I will mention here is you could flip these. Either way is okay. We could make the top no condom and the bottom condom. Typically, and I'm going to do it this way with condom on top, no condom on bottom, and I'll show you the difference as well. Because what we expect here is that not wearing a condom is going to increase risk for HIV. Typically, I would put no condom on the top, but as I said, either way is okay, and we'll see the difference in the interpretation in just a moment. So now it tells me 4,063 women completed the survey. So I'm going to put that in my bottom right. 788 indicated they were HIV positive. Where does that go on my 2x2 table?
A plus C.
And among those who were HIV positive, 355 indicated they used a condom at their last sexual encounter. Where does that go?
A.
And among those who were HIV negative, 1,598 indicated they used a condom at their last sexual encounter. So where does that go?
A
B.
plus B.
Oh,
It
So
goes in.
among those who were HIV negative, 1,598 indicated they used a condom. So I heard one person gave me the right answer.
B.
It is B. Yes, sorry. I was looking at it wrong for a second. Sorry, my screen stopped sharing again. So let me get that back up. I don't know why it's doing that on me. So that's because it gives you two. So among those who are HIV negative, that's this, tells me it's this column. 1,598 indicated they used a condom. So that's this row. So that goes here. So then now that I have that information, oh, why is it not showing up for you all yet? So that 1,598 goes in B. It's not showing up for you all yet, but hopefully it will in just a second. Goes there, and then you can fill in the rest of these by, let me stop the share and reshare it. No. Okay, well, my iPad's deciding to die out on me, so let me switch over to the computer and try to do some stuff with my mouse instead. So this is going to be much less pretty, not that my handwriting is pretty in the first place. So let me draw this out really quickly. So let me actually, so 4063 goes there, as we already said. And then we have 788 indicated they were HIV positive. So that goes here. And then we had 355 of those indicated they used a condom at their last encounter. So that goes here. And then we had 1598 that indicated that they were HIV negative and that they used a condom at their last encounter. So now that we have that, we can add up these numbers. So I can do 355 plus 1598. That equals 1953. And that gives me my total of people who use condoms at their last sexual encounter. And then if I want to get the number of people who are HIV positive who use no condom, I'll do 788 minus 355. And that gives me 433. And then the last one, to get the total number of people who are HIV negative, 463 minus 788, that gives me 3275. And then I do 3275 minus 1598, and that gives me 1677. So does everyone see how I came up with those numbers in there? And then I could fill in this last one as 2110. So now if I want to calculate my prevalence odds ratio, that's going to equal A divided by A plus, or nope, prevalence odds ratio, AD over BC. So my prevalence odds ratio is going to be equal to 355 times 1677 divided by 433 times 1598. So if you do the math, that equals 0.86. If it says to calculate the prevalence ratio, that's fine too. So you can calculate either one. I think on the exercise, I have prevalence ratio. So that's why I chose to, on the PowerPoint slide, do prevalence odds ratio. So if you did calculate the prevalence ratio too, that's just equal to 355 divided by 1953 divided by 433 divided by 210. And that equals whatever you all got. I won't calculate that out fully right now. 0.86 as well, so they're the same.
Yeah.
And that's mostly because the prevalence of HIV is pretty low in general. So what this tells me then is that those who used a condom during their last sexual encounter had a 0.86 times lower odds of having HIV compared to those who did not use a condom. So essentially, this is a protective factor, right? So wearing a condom protects against HIV. If, as I mentioned, over here, we put condom use on top, no condom use on bottom. If I had instead put no condom use on top and condom use on bottom, what we would have gotten is all of these rows, the rows and columns, the rows would have flipped, right? So now the bottom row would have been on the top row would have been on the bottom. So then my calculation would have flipped, and what I would have ended up with is 1.16 instead. So a flipped equals 1.16. What this tells me is that those who did not use a condom during their last sexual encounter had a 1.16 times higher odds of having HIV compared to those who did use a condom. So now it flips the interpretation and it flips the association, saying no condom use increases risk for having HIV at this moment in time. Does that make sense? So the exposure, it doesn't matter where you put it. It could be at the top or the bottom, but what changes is your interpretation. What you're always interpreting is whatever is on top compared to your first column. So in this scenario that we set up here, we're comparing those who used a condom to HIV prevalence. If we had flipped that, we would compare those who didn't use a condom to HIV. Any questions about that?
So pretty much just interpret like the top left corner of the chart, right? That's what you're interpreting?
Yes, exactly.
Okay.
You're interpreting the top left corner of the chart here. So
Okay.
condom use compared to HIV positive status. And that's almost always going to be the case. We'll see some different interpretations after the midterm, but most of the things that we do are going to follow this general format. You're going to use 2x2 tables for all of the different study designs that we're going to talk about after the midterm. So you're going to get really comfortable doing calculations using them and filling in these tables. So you have those additional sample problems that are posted on Cougar courses. You also have the sample midterm problems. And homework number 3 is going to have a scenario where you're going to have to calculate either a prevalence ratio or prevalence odds ratio or both of them and give an interpretation. So you're going to have multiple times that you can practice these calculations and ensure that you're comfortable doing them, because you are going to have to read a scenario similar to this and do fill in a 2x2 table and do a calculation and interpret it for the midterm exam. So what questions do you have for me before we end for today?
So on the midterm, the question will tell us which one to calculate, right? So it'll say calculate the prevalence odds ratio or prevalence ratio.
Yeah, for cross-sectional studies, it will specifically say calculate the prevalence ratio or the prevalence odds ratio. After the midterm, when we get into cohort and case control studies, it will not tell you. You will have to determine based on the type of study. But because there's multiple calculations for this, I will always tell you.
Thank you.
Mm-hmm. Any other questions that you will have? I hope this was helpful going through these calculations. As I said, you're going to see these on the homework. You're going to see these on the midterm. You're going to see these on the sample problems. We'll go over probably 2 or 3 more similar examples next week in the review session for the class for the midterm. And we'll go over multiple other sample problems to ensure that you all are feeling ready for the exam. So let me know if you need anything at all. Let me know if you want me to review anything specifically during the review next week, and we can kind of go from there. Don't forget about homework 2. I'll post homework 3 today and send you all an email about it. And we'll talk about a little bit the final project next week, since we have a few more weeks to work on that. But otherwise, have a great rest of your week and weekend. Do something fun. And as always, never hesitate to reach out if you need anything. Thank you all.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you. Have a great day. All right. I don't know if Andrew or Trent are still here, but I know. So yeah, if you have any, what questions did you have? Sorry, I'm forgetting how to pronounce your name again, and I don't want to mispronounce it.
Kanaya.
Kanaya, there, yeah. So what questions did you have about homework 1, Kanaya? And let me pull it up really quickly.
Okay.
Let me stop the